Hi, in this video we are going to talk about big O of nk solution for the problem of finding elements with more than n by k occurrences. Let's do a quick recap of the problem. Let's say we have this example, we have 30, 10, 20, 20, 20, 10, 40, 30, 30 and k is 4. N is 9, number of elements in this array. So what is n by k? N by k is 9 by 4, which is 2.5. So we need to find out elements whose count of occurrences are more than 2.5, which means 3 or more, right? Integer value. So the elements are 20 and 30. Our output for this example input is 20 and 30. The solution that we are going to discuss here is an extension of Moore's voting algorithm that we discussed in the majority element video. We are going to extend the same solution to make it more generalized for k occurrences, n by k occurrences. So the one fact that we are going to use in this solution is the number of elements in our result will not be more than k minus 1. Number of elements will be less than or equal to k minus 1. And how is it true? Let us see this with counter example. Let's say we have k elements in output. K is more than k minus 1, right? So let's say we have k elements in output. So every element should have n by k occurrences, more than n by k occurrences. So I'm just adding 1 to indicate it's more than n by k. So this should be smaller than or equal to n, total number of elements, right? I'm assuming k elements are there in the output and every element has to have n by k occurrences because it's part of the output. So it means you have n plus k is smaller than equal to n, which is not true, right? And if it is not true for k, then it's not going to be true for any other larger number as well. So this fact that we have written here is true, that number of elements in our output are not going to be more than k minus 1. Let us now see the algorithm and understand the algorithm step by step with this example. Like Moore's voting algorithm, this algorithm has two phases. In phase 1, we find out the candidate element, and phase 1 is by step 1 and 2. We have 3 steps, and step 1 and 2, they are phase 1. These 2 steps are phase 1 and this is phase 2. In phase 1, we find out candidate elements like Moore's voting algorithm, the elements which can be the possible output, right? And after we find out the candidate elements, this phase 2 or step 3, it validates whether these candidate elements are actually the output or elements or not. This step mainly checks that the k-1 elements that we have in the map, are they actually having occurrences more than n by k or not? If they have occurrences more than n by k, then this step is going to print those elements. Now, how do these 3 steps work together? So we first create a map in this algorithm, and the size of this map is going to be at most k-1 because we can't have more than k-1 elements in the output. Now we traverse all the elements, and for every element we do this. If this element is already present in the map, we are going to increment its count, right? 2.8. If it is not present in the map and map has space for it, right? If map.size is smaller than k-1, it means map has space. Then we are going to insert this element with count as 1. The third case, when this map does not have space and this is a new element, in that case we are going to decrease the count of every element present in the map by 1. And if count of an element becomes 0, we are going to remove it from the map, right? These are the 3 possible cases. We handle these 3 cases, and at the end we have candidate elements, and we check whether these candidate elements are actually output elements or not. Let's understand the algorithm step by step. So initially we have an empty map. We begin with I equal to 0, right? It's not there in the map, and map size is currently 0, so we are going to insert it. See, k-1 is 3, so map size cannot be more than 3. It can be at most 3. So we are going to insert this element with frequency 1. Then we come to next element. Next element is 10. So this is not there. So we are in case 2.b here. So we are going to insert 10. Then 20 again. It's not there, but map size has space. So we are going to insert 20. Again case 2.b. Now when we come to I equal to 3, we are at this element 20. We are now in case 2.a. An element is present, so we are going to increment its frequency. Now we come to I equal to 4. We again fall in case 2.a. We increment its frequency and its frequency becomes 3. Now we come I equal to 5, and this 10 element is also present. So we are again in case 2.2. So we are going to increment the frequency of 10 by 1. Now we come to 40. And this is the case which is not either this A case or B case, because 40 is not present and map is full. So what are we going to do? We are going to decrease the frequencies of all the elements by 1. So this becomes 0, so we are going to remove it. This becomes 1 and this becomes 2. That's our new map. Now we go to the next elements, 30. It's not there in the map, but we have space in the map, so we are going to insert it. 30, it's there in the map, so we are going to increment its frequency by 1. So 30's frequency becomes 2. So this is our final map. Now what are we going to do? We are going to traverse through all the elements in map, right? We are going to begin with 10. We are going to check how many times it appears. It appears 2 times, which is not more than n by k. N by k is 2.5. So this element does not appear more than 2.5 times. So we are going to ignore this element. Then we are going to come to 20. We count occurrences of 20 in the array. 20 appears 3 times in the array. And this is more than 2.5 times. So we are going to print 20 as output. Then we are going to come to 30. 30 appears 3 times in the array, right? Which is more than 2.5. So we are going to print 30 as well. So what do we do in the last step? We go through every item in the map. We count how many times it appears in the array. And if the count is more than n by k, we print it. Let us analyze time complexity of the solution. If we use an unordered map in C++ or use a hash map in Java, then how much time this particular step will take? So one thing is, if k is really small, then you can say nk is close to linear, right? And the thing is, in the earlier solution, we were creating a hash map or unordered map, which was going to have all the elements in the frequencies. Here, our hash map size or unordered map size is going to be at most k minus 1. And if k is small, say you have 1 lakh elements and k is only 10, then you are going to save space as well as it might take less time. So what are we going to do? We are going to traverse through every element. We are going to check if it is in the map. It's a constant operation. We are going to check if size is less than k and minus 1. It's also a constant operation. Putting is also a constant operation. But decreasing all the values in the map, it's not a constant operation. It's going to take theta k time. So we are going to have big O of k into n time by this particular loop. And again, we are going to traverse through the map and we are going to find out counts of all the elements. So we have k minus 1 elements in the map at most. And for every element, we are going to traverse through the array and we are going to see how many times it appears. So this is also going to take big O of nk time, because in the worst case, you will have map full, but you may have less elements. So overall time complexity is big O of nk plus big O of nk, which is big O of nk. Let us see how does this algorithm work. So the proof of working of this algorithm is also similar to Moore's voting algorithm. What do we do in this algorithm? We traverse through all the elements and finally we have some selected elements which are there in the map. So in this example, our map finally contained this. So these elements are the selected elements. I have written these elements here itself, right? 10 appears 1 times, 22 times and 32 times. And if there are elements whose appearance are more than n by k, then these elements have to be from this set. That's what we are claiming. And how is this claim true? So we need to show that none of the rejected elements can have occurrences more than n by k. None of the rejected elements. Now rejected elements are the all other elements except these 5. So I have picked these 5 elements from here, and this set of elements minus this set of elements is the rejected elements. So I just picked all the remaining elements. 1 occurrence of 10 is here, so I picked 1 occurrence this side. 2 occurrences of 20 are here, so I picked 1 occurrence of 20. 2 occurrences of 30 are here, so I picked 1 occurrence of 30 here and 1 occurrence of 40. These are the rejected elements. And how did they got rejected? They got rejected because when 40 came, it decreased the count of all the elements, right? It decreased the count of 10, 20, 30, and it rejected itself also because the map was full, right? At this point, when 40 came, your map had 3 elements inside it, right, with their counts. So map was full because k is 4, right? So we can't have more than 3 elements in the map. So 40 was not selected, and it also rejected 1 occurrences of all the present elements. So that's how these 3 elements got rejected and 40 also rejected. So one element in this rejected set rejects exactly k minus 1 other elements. let's say one element is the element which has rejected all the other elements, in all the cases, let's say 40 came every time whenever the map was full and it kept on rejecting the other elements. Let's consider the worst case. Even in the worst case, how many times this 40 will appear? How many times it will appear? Say every occurrence of 40 will have k minus 1 occurrences of other elements, right? So even in this case, how many occurrences 40 will have in this set? So 40 will have exactly n by k occurrences, right? Because one occurrence of 40 means k minus 1 occurrences of other elements. It can have at most n by k, not more than n by k. So that proves what we are trying to say, that no element in this set can have more than n by k occurrences, right? That's why we pick only these elements, we process these elements, and we try to figure out, do they actually have n by k occurrence, more than n by k occurrences or not.